Welcome you all to one more session. Here in this session we are going to see related to the counters. In the previous session we have seen up counting and down counting. Up counting means the ascending counting that takes place, whereas down counting is something where descending order of counting takes place. Now here in this session we are going to see both up counting as well as down counting that is set up under only one single device. Now let's see, that is up counting and down count. Up down counter we call it as. Now as you know that when we are performing a 2-bit up counter, the output of first flip flop was taken from positive end of my first flip flop and connected as clock input for my second flip flop. Whereas for down counting, the output of first flip flop was carried from negative edge of my, that is Q bar, output was taken as input for second flip flop. So that is what I am keeping the same concept here for up counting and down counting. Now as we need to perform up counting and down counting in one single device, so I am taking a controller here. Now controller I am representing it with M and Q as Q for performing the up counting, Q bar is for performing down counting, and this is my output Y. Now if you observe clearly the up counting as well as down counting, now I am considering this M, Q and Q bar as my inputs. So 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So 0 to 7 all the combinations I have written for my 3 input value M, Q and Q bar. Now my Y value. Now if you observe Y value, now for performing up counting I need to take M is equal to 0 to perform the value. Now M is Y, when Y is equal to Q, M value will be 0. I am taking first condition. Now when Y is equal to Q bar, M value will be 1 here. Now if you observe this, M is equal to 1, I am considering Q bar value. M is equal to 0, I am considering Y is equal to Q. Means M is equal to 0 for these values. M is equal to 0. I am considering my output to be Y is equal to Q, means Y is equal to Q. That is 0 0 1 1. So that's the reason I am writing my values as 0 0 1 1 here. Next, for when M is equal to 1 for these values, Y is equal to Q bar. So these are 0 1 0 1. So 0 1 0 1 I am writing here. So for the first set of 4 values I am performing Y is equal to Q, means I am performing a up counting operation. For Y is equal to Q bar I am performing down counting operation. So this is the logic table and the functionality table to perform both up counting as well as down counting under one device. Now you know Y value, output value. So let us calculate the Boolean expression for this Y. So this is the Y output. Inputs are M, Q and Q bar. M, Q, Q bar. 0 1 0 0 0 1 1 1 1 0, right? So I am mapping all these ones. So 1 is there for 0 1 0 and 0 1 1. So 1 is present is here 0 1 1 and is 0 1 0. Next one is present at 1 0 1, that is 1 0 1. Next one is present at all ones. So I am taking pairs. So my expression for Y will be Y is equal to A plus B. This is A, this is B here. Now what is A value? A stands for, now A stands for M bar Q. Now here A, left side common thing is M bar, and on the top the common thing is, this is Q Q bar, this is Q Q bar, right? So the common thing here will be Q. So that's the reason on the left side it is M bar. This is M. So the first value A stands for M bar Q. Y is equal to. Next value, that is for these value. Next value is M on the left side. On the top side, what is the common thing? This is Q bar and Q bar. So M Q bar. So my expression is Y is equal to M bar Q plus M Q bar. So this is the expression which is going to tell me when to perform up counting and when to perform down counting. So let us see now how this diagram looks like. Now this is the diagram. Now if you observe clearly, for doing performing up counting and down counting, Y is equal to M bar Q1 M Q1 bar. Now this setup I am setting in between the flip flops. Now These are 3-bit up counting and down counting. I am kept this setup here and I kept setup here. So I have connected for first AND gate Q1, for second AND gate Q1 bar. Say first AND gate Q2, second AND gate Q2 bar. Similarly, if I am having 4-bit, then the same setup comes over there. So in exam you might get either 4-bit value, 4-bit up counting, down counting, or 3-bit up counting or down counting. Now when a logic 1 is applied for all the flip-flops, now if you observe, the line has been connected for each and everything here. The outputs of this are connected as clocks. Why? Because this is the gate which is going to tell us whether to go with a positive output or negative output, right? So that's the reason the clocks are connected with using these setups. Logic 1 is connected and M logic is also connected for each everything. That is M and M bar both are connected here. So this is the logic diagram which is going to perform up counting as well as down counting in one single circuit diagram. So this, how did we get this one? Based upon our logic with the truth table which we have designed in the previous slide. So the next thing. So next thing is BCD counter or ripple counter. So what do you mean by BCD counter? The range of BCD numbers, you know, that is from 0 to 9. So for 0 to 9, if you observe from 0 to 9, I have kept my output as 1 here. Now BCD means it is a 4-bit number. So 4-bit number maximum value will be 15. So after 9, 10, 11, 12, 13 and 14, 15. For all these things, I kept my value as 0 output. So I need to get a expression for my BCD counter or ripple counter. So expression for my BCD counter. So I am drawing a K-map. First of all, I am drawing a K-map. Now while drawing the K-map, you know my input values are A, B, C, D. So my values are A, B, C, D. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? So my output expression is Y. So I am writing Y here. So the thing is, I need to represent this min terms here. So min terms are 1 from 0 to 9. So I am writing all ones here. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So I have drawn over there. Now the thing is, I need to look for the combinations. I need to make the combination. So this is my one combination. If you observe, this is my octal pair and this is my quad pair. For octal pair, on the top everything is getting changed. On the left side, what is the constant thing? A bar. So I am writing A bar. Y is equal to A bar. Now for this quad, on the left side the common thing is B bar. So I am writing B bar. On the top the common thing is C bar. So I am writing C bar. So my expression for my ripple counter is Y is equal to A bar plus B bar C bar. So this is the expression which relates a BCD counter. Means it should count BCD numbers from 0 to 9. That is what we are designing in this particular concept. Now let us see how the diagram looks like for our BCD counter. Now this is our BCD counter. Now this is my first flip-flop, that is second flip-flop. You have already got A bar plus B bar C bar. That one, the same thing have connected as a AND gate here. That AND gate along with my 4 flip-flops. A logic 1 is provided here and a logic 2 is also provided. A logic 2 is also provided here. Logic 1 and logic 1 both are connected as inputs along with a clock is provided. Now this Q0 comes as clock input, this Q1 comes as clock input, Q2 comes as clock input and Q3 will give as a output here. That logic, whatever the logic which you have given, we have connected with every pin of my flip-flops. This is what this is going to do. This is going to reset my counting operation whenever it reaches the maximum value 9. Whenever it is reaching maximum value 9, what it is going to do, this is going to clear all the values of my 4 flip-flops. Again it restarts the counting value from 0. So 0 to 9 it does the counting operation. After 9 it is going to reset or clear all the values in my 4 flip-flops. So this is the operation of BCD counter. Next, ring counter. Ring counter means the values are stored in a ring form. Now if you observe clearly, here the diagram, if you observe clearly, the diagram represents the ring formation of 4 flip. Now if you observe this one, this has 1 flip flop, 2nd flip flop, 3rd and 4th flip flop. The data is been provided as input here. The data comes out here like this. Now after this, the data comes here like this, data goes like this, and the data coming out of my 4th will come back like this and will attach here. Means this flow, whatever this flow is forming a ring here. This flow is forming a ring here. That's the reason what happening, this ring is this circular form, we are calling it as a ring counting. So that's the reason we call it as a ring counter. Now here 4 bits are there. So I am writing 4 outputs here. This is QA, QB, QC and QD. QA, QB, QC, QD. We have used only D flip-flops here. Now on first statement, at the instance of first clock pulse, what happens? Only first bit, the first bit will go as input here. Remaining will be 0, 0, 0. Next instance, what happens? This goes as, this 1 bit will travel to the next one, a 0 will remain here. Third clock pulse, what happens? This will travel to my third flip-flop, this remains as 0 here. At the 4th instance, what happens? This 1 will travel to my 4th flip-flop. On 5th clock pulse, what happens? This value will come and store at my first flip-flop again. So this becomes 1, 0, 0 and 0, right? So to come to the initial state, it is requires totally 5 clock pulses. So the number of states under ring counter will be, number of states is equal to number of flip-flops used. So totally to travel this 1 from first flip-flop to the last flip-flop, it requires a number of states, that is 4 states. Those 4 states are given by number of flip-flops used in your ring counter. So definitely you need to understand the flow of diagram with the help of these particular states. So number of states is equal to number of flip-flops used in this particular diagram. Now similar concept we are going to apply for the new thing, that is let us see the new thing. So this is our Johnson counter, similar to that of our previous concept. Now this Johnson counter, we are the same ring format we have connected, but the output is not taken from Q here. It is taken from Q bar. Q bar is connected as input for my first flip-flop here. Whereas in the previous case, we connected Q output as a ring form to my 4 flip-flop. Now if you observe, here on the first initial state, everything is 0. Second state, what happens? The first initial value come on to my first flip-flop. Remaining will be 0. On the third instance, what happens? This value will go on to the new second flip-flop and a new value will enter here. Right? On the third instance, what happens? This will move here, this will move here and a new value will appear. On 4th, 5th instance, what happens? This value will come here, this will appear here, this will appear on my second flip-flop and a new value will enter into my flip-flop. Right? Now here 1 has been stored on my 4th flip-flop. So here it is 1 as Q bar will be 0. So that's the reason on 6th instance of time, this 0 is getting traveled and settled back on my first flip-flop. And remaining values will be the same thing. This remains here, right? This remains here, this remains here, right? Now in 7th instance, what happens? This will travel here, this will travel here, right? This will travel here, this will go. On 8th instance, what happens? This goes on like this. Right? So the number of states in this my Johnson counter will be twice the number of flip-flops used. So that's the reason if you observe 4 flip-flops are being used. So the number of states, if you observe from top to bottom, it has taken 8 states to cover its initial position. So that is the reason twice the number of flip-flops used. Whereas in ring counter, the number of states is equal to number of flip-flops used. Whereas in Johnson counter, number of states is equal to twice the number of flip-flops used in this particular setup. So this is what related to Johnson counter. So with this topic we are going to end the counters topic and we are going to begin with a new chapter in the next new session. Okay, thank you one and all.